So we're going to take all of our skills that we did with solving for x in logarithms, solving for x in exponents, and apply them to real life situations. And there's actually a ton of real life situations that can be modeled with exponential and logarithmic functions. Exponential growth. Compound interest we've already talked a little bit about. The Richter scale. Did you know what happens when something goes up 1 on the Richter scale? Like an earthquake of 5? It's not great. We don't have any earthquakes here in our city, so we don't know really what it feels like. But some places have earthquakes all the time, and it's like, yeah, no big deal, no big deal. But then 5 to 6, a little bit more bigger of a deal. 6 to 7, a little bit bigger of a deal. 7 to 8. What happens each time you go up by 1 on the Richter scale? Does anyone know?
The ground shakes more.
The ground shakes more. How much more? Right? Like if this, okay, I will give you an example. If this is a 6, okay, this would be a 7. How much more did I move the desk? I moved it 10 times more left and right. If I did an 8.
Okay, let's not. Wait, do it.
No, I had to go 100 times more than I did the first one. I would have to go 10 times more than my 7. Each time you go up by 1. Each time you go up by 1 on the Richter scale, that earthquake is 10 times more intense.
You throw through the wall.
So a 5, you're like, it's not, it's shaking. But people are like, we would be scared because we don't experience it ever. Like, oh my goodness, the ground is shaking. I've never,
The highest number on the Richter scale.
There's no highest number. You could just keep going 10 times more. But what's the record?
Yeah.
There's been one, I think like 9 point, I think it's in one of the examples. 9 point something or 8 point. It's super, super crazy. Especially when you think of it being how much times bigger it was than some big ones. There was a pretty big one off Japan last week. So much that it started a tsunami warning. But from the results of that tsunami, nothing was major destruction, right? Like there's earthquakes happening every day all over the world. We just don't hear about them because they don't cause destruction bad enough that we worry about them.
So do we have like earthquakes here, but don't have ones?
Yeah, there is movement. The ground moves so little that you can't hear it. And same thing, another thing is decibels. But for decibels, instead of going up by 1, right? Every time you go up by 10, it's 10 times more. So something at 100 decibels compared to 120 decibels, you're like, oh, it's only 20 more. No, it is 100 times louder. 120 decibels compared to 100 decibels. And 120 decibels would be 1,000 times louder than 90 decibels. And so when so part of the reason that we have exponential logarithmic functions is when you have things that have such vast differences. Like we want to measure when it's just a tiny little bit. We even want to measure when it's so small we can, like, okay, the earth is moving here in Winnipeg, but we can't even feel it. Just something that's so extreme, right? So extreme that it's taking down buildings. I've tried to push down a building, never had any success. I've tried to grab the hold of the corner. And to think that the earth can do that on its own, that's crazy. So when things have huge differences in scales, we use exponential logarithmic functions to measure that. Okay? We have some decay, amount of drug in your body. That's a super interesting thing to talk about. Half-life of radioactive substances. Now, for each of these, there's formulas. And it used to be that on your formula sheet, you got a couple formulas and you had to know how to use them. They decided to take those formulas off of your formula sheet. This is actually a good thing for you. The bad thing for you is they can ask you anything. They could have like, the number of cell phones in the landfill is growing exponentially by the following formula, and make up some formula you've never seen before. But they have to give you the formula and explain what it means. That's the good thing for you. You don't have to memorize any formulas. For every single question here, they're going to give you a formula. First one we're going to look at is the compound interest formula. So if you got a compound interest question on your exam, they would give you this formula and they would tell you exactly what everything stands for, including that the rate has to be a decimal. It tells you that as well. Question? You need another one? Yeah. So then we take a question, determine the final value and I have some of these already pre-done. All you're going to do is plug in the numbers in the right spots. The thing about the compound interest formula that you need to know is how to put in the values of n, which I'll highlight right here. So in the formula you have n, which is number of compounding periods per year. In this question, can you see where it tells us the answer for this is 12 to put in? Okay, how do we know that that's going to be a 12?
Compounded monthly.
Compounded monthly. How many months are there in a year? 12. So, monthly would be 12. Here are some words that sometimes come up. Sometimes could come up weekly. What would you put in? 52. What about daily? 365. Annually, you would put in a 1. Semi-annually. That is, semi-annually is twice per year. This got a bunch of students maybe 3 years ago. It said semi-annually, they're like, how many is that? I'm like, I can't tell you on a test. All I can say though is if you put the wrong number, the worst that can happen is a half mark would go off. Right? So on your exam, if you don't know how to do something, you have a little bit of leeway in that you can make up a number and then do your work from there. There are some exceptions to this, right? You could have this question, you're like, I don't know how to do it, so I'm just going to write a equals 2 plus 3. I got 5. How am I doing? I didn't, my first part was wrong, but what about my answer? 2 plus 3 is 5. Should I get somewhere? No. If you oversimplify it, you will not get the marks. But if you make a little mistake in a number that like, I don't know what monthly means, I don't know how to do the ends, so I'm just going to put 7. Don't do 7. There's nothing that's compounded 7 times a year. I don't even know how you would try to say that. Yeah.
What was the one you said the other day? Bird?
Yeah, something with TH that I've said before. Don't think I'll ever say it again. Okay. So, A lot of these are fairly straightforward. Calculate the final value of $200, compounded semi-annual. Now, if you got this on the exam, they would give you the formula and describe everything. I just gave you the formula once. So we have a starting value of 200. We've got our interest rate 3% as a decimal. Semi-annually, you've got twice per year. Now, you should check with your calculator when you're studying. Can I get this value? Some common things. If your calculator, do some of you have when you hit the exponent button, does it do the little hat? Yeah. If that happens, and you have two things in your exponent, they need to be in brackets. Or you could do the mental math and write 10 and you would be fine. But if you just did the little hat and then went 2 times 5, it'll only do an exponent of 2. And then it'll say, because I do exponents first, then I multiply. Unless you do brackets. The brackets say you do brackets first. And then it puts everything in. If you have a calculator that lets you write it exactly as you see it, that is super, super helpful. Oh, we're gonna have some. I like today's lesson. I like this question because it introduces a lot of interesting math. First of all, those first 2 questions you probably won't get on the exam because they were just plug into your calculator, push enter. Super straightforward. They were just for us to practice plugging things in for them. This is the kind of question that you're going to get where it says, calculate the time. Why are we going to get this question? Because if I put things in, the exponent or the variable that I want to solve for, the t, is in the exponent, making this an exponential equation, meaning that you have to use logarithms to solve. So now our job is to find out what t is. So, how do you solve an equation with t in the exponent? Well, you want to take the log of both sides. However, if you can simplify your equation, you will make your life easier. Can you see that you could divide both sides by 30? And then this just becomes 2. If you can simplify things, it's going to be important because you'll make less mistakes with your log laws. You could have taken the log of both sides right from the beginning. It's not wrong. You just have more log laws that you have to work with. Now if I take the log of both sides, do you see that if I took the log of the right side, the exponent, I have a log law, that exponent could come out in front. I did this in one step. I didn't make a mistake. This one step would be worth 2 marks on most exams. Taking the log of both sides is worth 1 mark. Bringing the exponent out in front is worth a 2nd mark. But you have to be careful because I'm going to show you where students lose all their marks in this question. Okay, I'm going to write this in red. Do not write this down. I've seen students do this. They have this. They're like, ooh, I'm solving for t and exponent. I'm going to take the log of this side, and I'm going to take the log of this side, and I'm going to bring my exponent out in front. And this step that normally is worth 2 marks, you would lose both of those marks. Because I can't see that you took the log of both sides because you did 2 things at once. And you are not allowed to bring this exponent out in front because that exponent is only to this part, not to the 30. You'd have to do the log law that shows adding first and then bring the exponent out in front. So because you tried to do 2 steps in one and made a mistake, you have a possibility of losing lots of marks. So I often recommend just show that you take the log of both sides. Then if you screw up on your log laws, you'll at least get that 1st mark. Some exams taking the log of both sides they make a half a mark. It's funny because sometimes they're like, we want the exam to be out of 90 marks. And everybody's like, well, this is normally a 3-mark question. Well, this exam will make it 2 marks because we need to add up to 90. So we'll just skim a little bit. That sometimes happens though. But generally, the marking is pretty consistent. Okay, I'm going to erase that red. I hope you didn't write it down because it's all wrong. Now, I want to get this t by itself. Can you see that this is all 12 times t times this log? So the opposite of multiplying would be to divide by the 12 and the log to get the t by itself. Such a nice answer. Oh, 9.93. This is a nice answer because it opens up a whole bunch of discussion stuff, which is terribly fascinating. I like compound interest because I like making money by doing nothing. That is a fun, it's like, I think it's everybody's dream job. What's your salary? Right? What's your salary? Oh, I make 10,000 a year. What do you do now? Right? I'd actually like 7 of those jobs. I think I could fit them into my schedule. What are you doing today? Nothing. No, that fits all those jobs. Right? So compound interest is this idea. What is this saying? You have $30. And if you just do nothing, in 10 years, you'll have $60. Which is a little bit, it's not that exciting, right? But something fascinating is happening here. Let's do this question again. Who has more than $30? Okay. All right. Say an amount of money that you have. More than 30, doesn't matter what it is.
$350 in my bank account.
$350. So now we're going to do this with 350 here. If you wanted to wait until it doubles, what number would I put here? 700.
Ask Chloe how much she has in her bank account.
I'm gonna get jumped.
No, I'm serious.
You don't carry your bank account in your pocket though. So you should be okay.
Chloe, you got this.
Now, $350. If we do the $350, there would be 700 here. And if we simplified, what would the next step look like? Would it still be a 2? Yeah. It would still be a 2, and everything after this would be the same. So, I worked really hard. I did nothing for 10 years, and my $30 got to be $60. Brooke did nothing in 10 years. Her $350 became $700. You're better at doing nothing than I am, apparently. Which is fascinating because, let's just put this into perspective where we would like this. And I've been trying to get a sponsor so I could really show my students how important this is. I'm like, I just need someone to give me $1 million. I'm going to use it for educational purposes. I'm going to leave it in a bank account for 10 years to show my students that, look, it doubled. And then at the end of the 10 years, I'll give you your $1 million back. I have yet to find that sponsor. But the crazy thing is if I had $1 million, then over here would be 2 million, right? And if I simplified by dividing, wouldn't I get 2 again? And in 10 years, I would have made $1 million by doing nothing. Right? When I started off, you were like $30, like, oh, way to go, woohoo!
Yeah.
But $1 million, 10 years for it to double to 2 million? This is the crazy thing about compound interest. If you have, this is the problem with the doing nothing job. You need to have that lot of money. That's where most of us are like, yeah, I'm missing, I can do the rest. I can do the rest of the doing nothing pretty well. I just need that big amount of money to start with. But if you have that, it takes the same amount of time to double. And what's really cool in this question is I'm going to teach you the rule of, this is about as inaccurate of math as you can imagine that works out to very complicated questions. Okay? So we did all the appropriate work with logarithms, needing to get to all the way to grade 12 pre-calculus to figure this out. Okay? And someone comes along, oh, I just use the rule of 72 or sometimes 70, depending on how I feel. That sounds like not a very accurate rule. And then they're like, well, how does that rule work? Well, I take my interest rate and I either do 72 divided by my interest rate or 70 divided by my interest rate. Just whichever the math is easier. So if you had to divide by 7, would you use 72 or 70? 70 is easier to divide by 7. What's 70 divided by 7? 10. Oh, it'll take about 10 years to double. How accurate is that? It is the craziest simple math thing that replaces a super complicated math thing that works. If you had an interest rate of 8%, I would use 72 because it divides nicely by 8. How long is it going to take to double? 9 years. About. We could do the math, figure it all out, and it would be close. But what's really nice about the rule of 72 or rule of 70 is you can actually go, okay, I know that I'm putting my money into this GIC, it's giving me 5%. Which one divides nicer by 5? Probably the 70. 70 divided by 5, 14. I will double my money in 14 years. Which is super cool. But 5 to 7%, look how much quicker it doubles. 10 years to double instead of 14 years. Right? That 10 years, that extra 2%, you can take a holiday from doing nothing for 4 years. Or you could just keep doing nothing and make even more, even faster. Because it's going to double again in 20 years. That 1 million that becomes 2 million is now 4 million if you decide not to take it out for 20 years. That's crazy. That's the power of compound interest. I'm still waiting for that benefactor who's really concerned about grade 12 pre-calculus students who would really benefit from seeing how I actually made $1 million doing nothing. Right? All right, here we go. Andrew, you're investing in an RSP. The interest rate was 5% compounded. Ooh, we didn't do this one quarterly. What do you think the end's going to be for quarterly? 4 times a year. The RSP is now worth $2,500. How much did you originally invest? So we need to plug everything into this formula. Do you need logs? No, why not?
It's not in the exponent.
What we want to solve for is not in the exponent. Right? So just because there was an exponent originally does not mean you need to do logs. You would just have to get the p by itself by dividing. Type this into your calculator. So this type of question doesn't come up very often because it actually needs no math from grade 12. So instead, you're going to get questions that ask you to use logarithms. I'm going to leave the next question for you to do on your own. If you do it on your own and you look at it, I'll click the boxes so it briefly shows up on the video so you can double check your work later. But we'll skip the next one and go to the last one. Yes. Yes. Okay. So this one we're gonna skip. You can check it later. I did it by taking the log right away. There's the answer, but we're going to do this one. Because this sometimes happens on the exam, and people forget our doubling example. This is at the bottom of the page. People forget the doubling example. The important thing for that doubling example that I did is, did it matter how much you started with? No. It took the same amount of time for 1 penny to double. 10 years later, like, oh, I have 2 pennies. Or if you had 10 million, and 10 years later, you have 20 million. Oh, that's all. That would be a good thing. You can just live off interest. Be so good. Okay? Unfortunately, if that was true for everybody in the world would probably fall apart. Nobody be working. We'd all be doing nothing. Go to the grocery store, there's nothing there because nobody did anything. Anyways. So, calculate the time it would take for an investment to triple if it is compounded monthly at a rate of 5%. So because it doesn't tell you the amount, some people get stuck and say, I don't know what to do. Pick any amount, right? I picked $1. When it triples, I will get $3. $1 is really nice because you actually don't have to do any simplifying. If you want to make your life difficult, start with $15.35, right? Triple that. And then if you divide later, you're going to get 3 equals no matter what. Now we're solving for that in the exponent. So I could take the log of both sides, bring my exponent out in front, divide. $22 years for it to triple. What's that?
That's a long time.
That is a long time at 5%. Now we're getting greedy. Oh, I don't know if I can wait 22 years to do nothing to triple my money.
But if you added 1 cent every month.
Oh, that could add up too. In fact, we're going to learn how we can use programs online to play around with ideas to see how much money we could make. More likely though, we're going to take those programs and see how much money we're going to end up having to pay. Because in real life, the chances of you investing money are much more unlikely compared to the chances of you having to borrow money. You're going to get a job. That job is going to require you to have a car. But you can't afford a car because you don't have a job. But you can't get a job unless you have a car. Oh no, what's going to happen? Well, you borrow money to get the car, to get the job. Use the job to pay off the money to get the car. But in the meantime, somebody else who gave you the money, aka the bank or the loan shark, is collecting interest from you. We're going to look at that in a bit as well. Terribly fast. Okay. So, here's our next formula that we're going to work with. The continuous growth formula. The continuous growth formula is actually the compound interest formula. But if they said, what happens if we paid your interest instead of monthly, we gave you interest daily? And you're like, oh, this is better. And then they're like, well, what happens if we paid you every hour? You're like, oh, that's even better. What happens if we paid you every second? Even better. And this would be like, what happens if we just continuously, like every little millisecond, we put money into your bank account? How would that affect things? Well, the formula changes to this, where E is the number E, 2.718. I call this formula the PERT formula, because it says PERT in the end. But and it looks at continuous growth. Now, no bank will pay you interest every second, okay? The nice thing about more compounding periods is that you get money more often, and you can make interest on the money you get more often, and we'll see what that does. Okay? In fact, here's our first example, and we're going to compare. You put 2,000 into an account, 5.5% interest, 10 years, and we're actually going to start with B. If it was compounded quarterly, that would be our old formula. You plug everything in, and in 10 years, you would have $3,453.54. What does it mean when it's compounded quarterly? Well, they would figure out what interest they owe you every 3 months and pay you that. And as soon as they pay you that, then you start making money still on the original, plus the interest that's added, you make money on that as well. So you only start making money on added interest after 3 months. This one, they pay you, like, as soon as you put money in, your bank account starts increasing by a bit. And if that happened continuously, this number is going to be bigger than this number. Are you ready for it? You are going to be surprised. It's only like $12, $13 more. Are you not surprised? Didn't you think it was going to be like a lot more? Only and this is in 10 years. Okay. Why is this not a lot more? Well, I'm just going to show you the comparison. Okay? How this works. If I do 5.5% of 2,000, that means that if you waited a whole year, that's $110 in a whole year. If I divide that by 4, that means after 3 months, they'll give you $27.50. If instead of continuously, I just checked out every second, okay, so $110 in a year, divided by 365 for days, divided by 24 for hours, divided by 60 for minutes, divided by 60 again for seconds. That means that every second, they're going to give you this much money, which is basically nothing. And then in the next second, you are going to make interest on that money as well, which is basically nothing. So breaking the compound periods up more often doesn't actually change the amount a lot. In fact, it probably plays more with heads than anything. So banks will be like, oh, this bank charges you daily. You should come with us. We only charge you interest every month. And you're like, oh, you could get swayed over. But their interest rate is 0.25% better than yours. Oh, but they charge you daily. That's why. That percentage rate is the huge factor. How often it's compounded makes, yes, a little bit of a factor, but here it was like $13. I changed this question to, I'm going to do the same thing. I'm only going to add 0.25% interest. 1 plus 0.0575 added 0.25 divided by 4 to the exponent of 4 times 10. Just adding 0.25%, changing it from 5.5 to 5.75, $3,539, almost $100 difference by adding 0.25%. So the percentage rate, you take one thing out of here, the percentage rate is huge. You're buying a car. You can probably, maybe the person selling you the car doesn't really know the math. This could happen. You're like, come on, buddy, you could lower it 0.5%, like half, it's not very much. If you convince them to lower it 0.5%, you're gonna save yourself hundreds and hundreds of dollars. Right? The bad strategy is, come on, let me save diet $2,000, please. They're like, no, that's a lot of money. But if you do a little number like 0.5%, and we're gonna see that that makes the biggest difference. Okay. We're gonna skip to go faster. We're gonna skip the next two. I'm gonna leave these for you. I'm going to put the answers up here. You'll notice with the PERT formula, though, one thing when solving for something in the PERT formula, we tend to use the natural log a lot, because when you get the natural log of e to what power is e? It's 1. So it makes that go away in a question. So you'll notice when if you want to watch this video later and see these ones, you'll notice when I solve them, I use ln a lot because the question had an e in it. You could still use log. It gives you exactly the same, but you just have, here you'd have a log e on the bottom and you type that into your calculator and it works out perfectly fine. Okay, here is the place where population growth is where the continuous formula is used a lot, because I'm gonna get really happy and really morbid for you guys for a moment. Okay, you wanna be happy first or morbid? Morbid. Morbid first. Okay, since we started this class, like tons of people all over the world have died. Seriously. Death.
What was the happy parts of result?
There's been a ton of babies born. There's a little, like if we put all the babies that were born in the world since class started till now, it'd just be like pure mayhem in here. Crying, bubbly babies. And like probably fill this, I can't, filling this whole classroom with babies right now is like too much for my brain, but yeah, lots of babies being born, happiness, right? So we got sad things happening, positive things happening. As a result, it's hard to say what our population is doing. It's always changing. And so the best model is to say it's continuously growing because every millisecond something's like happening. Okay.
Do you only use natural law when there's an e?
No, you can use it
Whenever
you want. In fact, after grade 12 pre-calculus, once you get to university, you almost never use logs again. ln becomes the one you use the most in calculus. Yeah.
Probably ln always now.
Well, because we learn logarithm and log sounds like logarithm, it just is an easier entry point.
You could just like never teach anybody about log.
I could, but you need to know logs of all bases
Yeah.
anyway, so you still need that.
Okay.
Okay. So, with continuous growth, we can model it with a PERT formula. Of course, it used to be that the PERT formula was on your formula sheet. So you would have to recognize that as soon as a population question had continuous that you'd use this formula. Now they will give you that formula on the exam and say, hey, you have to use this formula. This is what things stand for. So find the projected population in Vancouver to the nearest 10th of a million. Well, you plug in your initial amount, 1.38 million, your rate as a decimal, the time with E, type it into your calculator, no problem. And we get 2.3 million. So these models are very important for cities, for countries. They make a population growth model and they go, uh-oh, if we keep doing what we're doing right now, we could run into problems. Okay? And it's actually these models have completely changed societies. Okay? For example, in China, they did a model X number of years ago and said, uh-oh, our population is going to be too huge. So they made a policy that families can only have one child. It's illegal to have more than one child for the longest time. And now they're running into the opposite problem. They don't have enough people that are young. So now you get like bonuses. Now it's the opposite. You have multiple kids, will give you bonuses. All right, we'll continue this tomorrow.